Hello there, welcome to the Learning of Engineering Tutorials video lecture. In the last video, we have seen how to construct the shear force and the bending momentum diagrams for the cantilever. At the same time, we have developed a mathematical model in order to draw the shear force and bending moment diagram. In continuation of that, here I took the same cantilever beam. Now we have taken some numerical values and which the member is going to be subjected to the transverse loads as a point load. There we can see the beam is going to be, or the length is going to be, AB is going to be considering, and at the same time they are at the different positions, the point loads are going to be acting. At B, at C and at D I have given the notations in order to recognize the situation. At the B is the 800 newtons, at C is the 500 newtons, at D is the 300 newtons. Now they are located at different positions. There you can see from the end A, the D point is located at the 0.5 mm. It means the 300 newtons is located at 0.5 meters, right? And point C is going to be located at 1.2 meters, that is 0.5 plus 0.7, that is the 1.2 meters. And the point B is going to be located almost is the 2 meters distance. It means the length of the span is the 2 meters, and at the different locations the point loads are going to be acting. Now what is our main goal? What we want to do over here? We need to find out the shear forces as well as the bending moment at any section of the beam that we need to be find out. Because we know the engineering members, the beam is the engineering member we are widely using for the different applications. There we can use in the automobiles, or we can use for the civil structures, or we can use for the aeroplane structures or the aerospace structures also. The beams are going to be widely using. Some are finite beams they are going to be using in terms of the length point of view. So that's why the understanding of the forces, how they are coming and what is the behavior of the beam is the utmost important. So now we can see how the shear forces are coming to this part. Already we know the shear force we define the algebraic sum of the transverse forces acting on a beam towards the right side or left side we are going to be considering. Now I am going to be taking, because from the point B, because we are not drawing any free body diagram for the cantilever beam, it means that it doesn't require the identifying the reaction forces at A. Without identifying the reaction forces, we can understand we can calculate the shear forces as well as the bending moments. Now we can see here the shear force I want to be calculate. So I am going to be starting from the point B, then I will move to C, then D, and finally I will come to at the point A. And similarly the moments also the same order I will try to follow. So now I am going to be taking the shear force at B is equal to how much? When I am going to be considering the point B, I only to consider at the point B and right side the forces I have to be considered. So when I am going to take the point B, I am omitting all the left hand side of the part. I will take only to the right side of that part. So then the point B, how many forces we do have? 800 newtons force is there and there is no forces in the right side. So that I am going to be taking 800 newtons. Right? And similarly at the point C, and it is located at some distance we do know. And similarly, how many forces we do have? When I am going to be considering the point C, I can consider only the right side portion of the beam. So how many forces we do have here? At the point C, one force, and the right side another force is there. Totally the two forces we have to be considered. So that's going to be the force C is equal to here 800 plus 500. So that is equal to 1300 newtons. Clear? And similarly at point D and right side portion of the beam, three forces we do have. And that I am going to be taking here is the FD. Sorry, that is the FD is equal to 800, 500 plus 300. So that's going to be 800 plus 500 plus 300 is equal to, that's going to be 13 plus 3, 1600 newtons. Can you see here? And now I am going at the point A. So what is the shear force at A? The shear force at A, how many loads are acting from here? Towards the right side, 3 forces are acting. So that's same magnitude at the point D. So that's going to be 800, 500 plus 300. There is no load at point A, that I can say this is also 1600 newtons. This is the way we are calculated the shear forces acting on that member, because the shear force is trying to shear the object in the transverse direction to the axis of the member. So that the magnitude we can see, the maximum magnitude existed at the point D as well as at A. It's going to be clear that chances are there the failure is going to be occurred. That means the maximum stresses are may be built over this point. So now we need to find out the bending moment. So we know the bending moment is equal to force into perpendicular distance, right? So here also I can consider algebraic sum of the moments of the transverse forces acting any section of the member, and to the right side or the left side we have to be considered. Now my solution here, I am going to be considered to the right side only. So now I am going to take the moments at B is equal to, we know the force into perpendicular distance, the line of action of your force, and the point of observation that I am going to be considering. That's going to be 800 is going to be the force, and which is coinciding with your observation point. That's going to be 0. Then I got it as 0. And similarly, next point I am going to be shifting to the next section of the beam. That is the section here I can consider the C. Now can you see how many forces will you have to the right side? 800 and 500 at the point C. Now I want to find out the bending moments which are acting at the point C. So that's going to be MC is equal to, and forces are going to be 800 into the distance is going to be 0.8 plus or minus, that means I am going to be considering here, suppose the plus 500 into 0. Now the value of here, the 500 into 0, then finally MC is equal to 640 Newton meter, we got it. And similarly, we need to find out the bending moments at point D. Just can you see, I am shifting from a right side to the left side of the each point. So the D point is there, that's going to be the moments at D is equal to. So the D is equal to how many forces will you have? 1, 2, 3 forces. And it has at a distance, it is going to be existed to the line of action to the observation point. That I am going to be taking 800 is the first value, and here is the 0.7 plus 0.8 is going to be 1.5 meters plus 500 into 0.7 plus 300 into 0. So if I am going to do the calculations, 800 into 1.5, 500 into 0.7, so then the magnitude I am going to be saying here, that is equal to 1550. So that is value is the 1550 the Newton meter. And C. So now we need to find out the moments at A. So that's the moments at A is equal to, so moments at A is equal to 800. What is the distance? This is the line of action and this is the point. So that is the 2 meters plus 500 into what is the distance here? That's going to be 1.2 meters plus 300 into 0.5. If I am going to be add all these values, I got it around 2350 newtons meter. 2350 Newton meter we got it. There we can see these are the magnitudes we got it. Then what is the sign conventions we have to be considered? There we can see when the shear force I am going to be considering, the downward direction is going to be the positive, upward direction of the forces are going to be the negative. Now can you see in this figure 300, 500 and 800 are acting in the downward direction. So then I can consider that is the positive. But when it comes to the bending moment, I can say when it is going to be acting in the clockwise direction or anti-clockwise directions. So here I can consider, so anti-clockwise direction is the positive and the clockwise direction I can consider as a negative. So can you see? So in this case, what are the forces? When the point B, it is going to be 0, and at point C, can you see 800 into 0.8, it is trying to move in the clockwise direction. At the point D, the point C and the B loads are going to be acting in the clockwise. It means that all all these forces with respect to the observation point, they are moving in the clockwise direction. So I can get here is the value is going to be the minus, and here is the minus, and here is the minus. Alright, so on that basis I can draw the shear force as well as the bending moment diagram. So here is the procedure in how to draw the shear force as well as the bending moment diagrams. So from each section of the member we need to draw the extension lines, and similarly from the point B, extension lines, that's we can show with the dotted also. So once the extension lines of these lines are representing the section of the member. So now I am going to be taking here is the horizontal, and similarly it is representing the axis of the member. Can you see here? Yeah. So this is the way we are going to be draw the. So once the axis of the members we have drawn, now I am shifting these shear forces and bending moments to here. The first one I am going to be trying to find out the shear force, and here is the bending moment. Now what is the value at point B, right? So at point B it is going to be around 800 newtons is there. So this is going to be the point B, right? And at point C it is going to be 1300 newtons are there, and we have to take the scale over here. So suppose 800 newtons are there, so then what I am going to be taking, the 5 centimeters or 10 centimeters is equal to 200 newton meter. So accordingly on the scale basis we have to draw this one. So here is going to be your 1300, and similarly, and we are getting here is the 1600, and here also the 1600 suppose, right? So what I am going to do, I am going to draw. Can you see at the point B and C there is no load, there is no load between these two, and C and D there is no load, and D and A there is no load. It means that the line between the points are going to be getting in the horizontal direction. So this is going to be your vertical line, which is representing the 800 newtons, and from here I am going to be draw the horizontal line, and I will construct it over here. So this is going to be the 1300 newtons from this point to this point, and here is going to be 1600 newtons. So that points I am going to be taking here. There is no load, and load is going to be acting here. Sorry, and here it is going to be the point over here. So 1300, and from here the load is going to be coming like this, and finally it is. Can you see? It is forming like a step system. So here at the point B, 800, 1300 at C, 1600 at D, and A also we are getting the same value of the 1600. So we got it here. So this is going to be your shear force diagram. And similarly, we are going to be taking the bending moment diagram. So how could you draw that part? Now we are trying to plot the bending momentum diagram. At point B, it is going to be 0. This is the point is equal to 0. And after at MC, that is going to be the point here, it is going to be around minus 640. It means that the below the axis of the member that I have mentioned. So this is going to be minus 640 Newton meter we do have. And similarly at D, it is around minus 1550 is there. So that I am going to be considering here minus 1550 Newton meter. And similarly at A, it is minus 2350. So that I am going to be taking over here. Alright. So I am going to be joining this point with here. Can you see the order of the curve? In this case, between the point B and C, there is a horizontal line is there. It means the shear force is going to be constant between the points B and C. So here I am going to be getting the inclined line. And similarly, between the D and C also same phenomena, I will draw over here. And similarly, from the point A to D, that I will get it here. So this is going to be representing your bending momentum diagram. So I hope you are able to understand here how to construct the shear force diagram as well as the bending moment. If I want to find out the shear force over here, so that's going to be the point E. So then what happened? I am going to be extending the line over here. Oh, then I can find out the shear force over here. and then on the bending moments I can measure over here and by using the scale. So this is the way it is helping at the instantly we can calculate the bending moment as well as the shear forces by using these diagrams. So in continuation of this one, we will do one more or two problems in coming video lectures. So I hope you are able to understand the concept here. So stay tuned. Thank you.